Much for introduction. So it will be my talk will be in addition to very nice talks which were on the first day of the summer school about plasmonics, particularly nice talk of Olivier Plucheri, and I will. This talk is the result of collaboration of two scientific groups. One group from Tartu Institute of Physics and another group from Tallinn University of Technology. So in Tartu we are mainly work with laser spectroscopy of fluorescent materials, optical properties of noble metal nanoparticles. And in Tallinn group, they work mainly with preparation of solar cells, so they are experts on solar cells, and we try to combine our efforts to see how we can improve the work of solar cells by means of noble metal nanoparticles. So, in the beginning, I shall speak about the types of solar cells and solar cell generations, like an introduction to the topic. Then remind the simple principles of solar cell work. I will say more about inorganic solar cells. Then, of course, about the optical properties of nanoparticles to see how they can influence on solar cell performance. Then about the general approaches or principles to plasmonically enhanced light harvesting, and finally conclusions. Conventionally, we can divide solar cells on several generations, and first generation is silicon-based solar cells. They are the most efficient, up to 20% efficiency, but they are the most expensive also, because we need high-quality crystalline silicon material. Saying about the second generation, people try to make material more cheaper. It means use amorphous silicon and thin film layers. So in this case, we can say about the amorphous silicon and other semiconductors like copper indium selenide, copper indium gallium selenide, cadmium telluride. And these materials are arranged in thin films. It means we can economy material and deposit it on the flexible substrate. In this case, we obtain more cheaper energy, but efficiency is also less than for crystalline silicon. And today, the most perspective direction is creation of third generation of solar cells, which are combined several advanced technologies, like, for example, cascade solar cells. It means that when you have several thin layers where each layer absorbs certain part of spectrum of incident light, and then rest of light transmitted further, and next layer absorb next part of light, and so on. Also, promise technique, solar cell concentrators, when you use some special reflectors which will focus light in some special points, which will increase light harvesting, and plasmonic solar cells also included in this third generation. So, reminding the principles of solar cell work, if we imagine PN junction excited by incident light, here we have a depletion region which is created by partially migrated holes in this side and electrons in this side. So this depletion region just to avoid further further migration of holes here and electrons here. But when we irradiate this junction, we create electron and hole pairs, and under the action of this depletion region, we obtain situation when holes migrate to this side and electrons migrate to N region, and finally we obtain some useful current which we can use in some load. Of course, for efficient work of such system, we need to satisfy several requirements. Absorption of our material must be quite high to obtain like more conversion light to electrons and holes. The barrier here also must be high for separation, for nice separation of electrons and holes, and we must provide a good transport for the charge carriers here and here, and avoid ohmic losses or short circuit in our system. Therefore, practically, especially in Tallinn Technical University, they prepare such multi-layered structures to satisfy all of these requirements. And for us, the most interesting layer is absorber layer, the layer where we can generate charge carriers. And usually when we use thicker absorber, we have more absorption. If we use thinner absorber, we have less absorption. And if we consider situation, you see when we try to decrease the thickness of absorber layer, for example, from 500 nanometers to 100 nanometers, you see that we have also decrease in absorption, especially in the red and near-infrared region. And the idea that it would be nice to have some dopant to our absorber layer, which will provide us some selective enhancement in absorption here, which will compensate this situation when we come to thin film absorbers, to second generation cells, but we will have possibility to save absorbance here in this region. And it appears that noble metal nanoparticles are good candidates for such kind of dopants in the absorber layer. And now a little bit to properties of particles. It was mentioned earlier, but I just remind you some features. So from ancient times, it is known that dispersions of noble metal nanoparticles, silver and gold, can give color to the liquids or transparent solids, to the vessels or to the color glasses. What's happened in this case, when we have incident light on the nanoparticle, this light can be scattered and can be absorbed. And in this case, we have correspondingly scattering and absorption cross sections. Here is a little bit mistake because it must be minus. So total extinction is composed from absorption and scattering. And as was said previously, resonance condition appears when dielectric permittivity of particle itself. For dipole case, when we have dipole, small particle which can be considered like a dipole, we can imagine that resonance will be when epsilon of particle will be minus 2 epsilon of surrounding. And if you are not working with optical properties of metals, first time meeting this, like people say, very amazing why we can, from this equation we see that permittivity of metal can be negative, how it is possible. Because in electrostatic field, usually when we say about permittivity, it's positive number which show us how strongly external field can be decreased by the medium because of polarization of this medium. But in case of metal, if we consider very simple model like free electron plasma inside the positive lattice of nucleus, then we can say that such system also will have permittivity. And if this permittivity positive, the system will behave more like dielectric, but if it is negative, it will behave more like metal. And how it can be imagined, the particle which is situated in the periodic electric field of incident light, for example, they will obtain polarization. And you see, since we have change in electric vector here, we have also change in polarization. Here it's directed in this way, here it's directed in this way. So we have oscillation of electron in the periodical field. Even if we switch off the external field, we still have this polarized situation. And if we consider one electron, on this one electron we will have influence of this surface charge which formed in this particle. And this situation can be described by just simple Newton law, when we have acceleration of electron and we have external electric field from these surface charges. And finally, if you try to solve this equation, we will come to the so-called plasma frequency. It means own frequency of this surface charge which we have in this particle. And it depends on the charge of electron, concentration of electrons, mass of electrons. So, and if we come to the permittivity of material of this particle, we will obtain such value. And you see that it can be it can be positive when the frequency is very high. It means usually it's for UV light. And if you consider the most close situation to these free electrons, it's usually for alkali metals in such situation. So the electric field can penetrate inside the medium more, and in this case permittivity will be positive. But in case of negative permittivity, we can imagine when the frequency lies in visible range, and in this case, because of this ratio, we can obtain negative number. So when we have more metallic behavior, the whole field almost not penetrate into the medium and just reflected. But when we say, you remember when we say about the gold, we have some interband transitions. It means that our electrons in gold are not completely free, but we have some strong influence of also from bounded electrons, and therefore we have coloration of gold. And saying about suspensions, we can for deep dipole situation for small particles, we can say that okay, if you have dependence of permittivity for gold on the wavelengths, from this resonance condition we can say permittivity of medium, for example for water, will be such, then we can find permittivity which will be needed for resonance, and then plot on the graph found this point for this permittivity and see what wavelengths we will have as a result. So here we have near bluish greenish wavelengths. It means that this light will be strongly absorbed, and the rest of light means reddish part will be rest, and we can see therefore red appearance of the gold colloids. And on the spectrum also it's illustrated by the such plasmonic band in absorption for small particles. For silver resonance, if we use the same principle, have the epsilon of medium and try to find resonance epsilon and see what wavelengths will correspond to this resonance, we see it's near violet. Therefore, this part of light will be absorbed, and the rest one we will, like yellowish, reddish, we will have such appearance of silver, small silver nanoparticles. As I said before, total extinction composed from the scattering and absorption, and of course these two components will be different for different particles with different sizes. It means bigger particles will more scattered light, and smaller particles will more absorb light. And both of these effects can be used in solar cells. Firstly, I will stop on the light absorption, as was mentioned, and we return to the situation when we have this absorber layer, and we can use such kind of selective extinction of light to increase absorption. But here we must clearly separate situation when we have absorption in the particle itself or absorption in the material. Because when we have more absorption in the particle, it's just waste of energy on heating. Because external light just will heat our metal, but will not influence on the host medium. But for us, it is important the influence on the host medium. Therefore, when we compare influence, plasmonic influence, we will say that reference material just neat absorber layer, and absorber. Let's say when we say about enhancement, we will see such situation. It means that we will take into account absorber with electric field created by the nanoparticle. Since this electric field also has resonance nature, we can see that in the plasmonic spectral plasmonic diapason, we will have situation when this local field will be very high, and because of this high local field, we can obtain also higher absorption in the host material. And indeed, if we simulate situation, here you see dot line is absorption in the neat absorber layer, and this area under the green, it will be absorption in the medium, in the host medium, which have inside plasmonic electric field, locally enhanced. And this brownish is the absorption in the metal itself. It means that it's not useful for us, but here it's marked also. And if you compare the area under this dot curve, this area under this green area under this curve, we will obtain like almost 2 times enhancement in absorption. And it was, at least theoretically for us, it was very interesting, and we submitted this result into the energy procedure. It was the conference where we submitted it. And here, if we say about different metals, you see that here this silver, gold, and copper, they are plasmonically active metals, but aluminium is not active. And you see that for aluminium we don't have such effect. And if we compare the dependence of this absorption enhancement on the particle diameter, you see also we have some optimal diameter for the particle, because if you have higher particles, they are more scattered light, and local field in this case will be not so strong. Therefore, we don't have enhancement in the material. Even more, we can make generalization of situation to the more amount of particles. It means if we have not 1 particle, but for example 2 particles, and analyze situation for 2 particles, we see that it will be dependent, of course, on the distance between these 2 particles. But if we try to calculate this absorption enhancement, it will be that if particles are very close, like 30 nanometers between them, we will have interaction between these 2 local plasmons, and because of this we will have some shift of resonance band to more reddish one. But if the distance between the particles is near 100 nanometers, we still have quite nice plasmonic enhancement, and we can say that if we add more particles to our system to satisfy conditions that it will be not very close to each other, we will have nice plasmonic behavior for such absorber. And coming to the experimental realization of the system, we plan nearest time to try to do it just when we have, for example, thin gold film on the substrate. We can heat it and very quickly cool it. As a result, it will be melting, and after this melting, we can obtain some metal islands on the surface. And on the top of these metal islands, it is possible to deposit this semiconductor absorber layer, and we will try to do it and compare the theoretical calculations with experimental results. What is other experimental technique which is accessible in the Tallinn Technical University? They can make so-called spray deposition of coatings. It means they have substrate which is immersed into the like surface is free, but body of the substrate immersed into the melted metal, and it is possible spray precursor, for example, containing gold nanoparticle, not nanoparticles, some gold salt, with precursor of this semiconducting material, and finally, after spraying, it will be immediately annealed because of high temperature of this substrate. And by such a way, it is also possible to obtain some composite material, semiconductor plus nanoparticles. But at the moment, they have a problem that if we use some chloride salt of the gold, this chloride reacts with semiconductor, and we must think about the possibility how to avoid this reaction. It is possible also, like a variant, we're thinking about a situation when we have a coating, some semiconducting coating, and here we used first time like a model titanium dioxide, then deposit this solution of gold salt on the top of this coating and then heat it. And as a result of heating will be thermal decomposition of this salt, and these particles will be ground on the top of this semiconductor layer. This situation is also can be useful because when the particles are situated on the top of layer, it is possible to have such situation when the incident light particles will be bigger, and incident light can be scattered inside the structure, and this scattering inside will be higher than scattering outside. And by such a way, by such multiple scattering, it will be possible to obtain situation when this traveling light have more possibility to absorb, for absorption. And this also will increase absorption in our absorber layer. And to model this situation, it was prepared such type of materials when these gold particles was grown by thermal decomposition on the top of the titanium dioxide film. And you see that depending on the concentration of this gold salt, we obtain smaller or bigger particles, and shapes are quite different here. So regulation or adjustment of concentration for the gold solution, we can regulate the size of particle. And to examine plasmonic absorption in this system, we measured optical transmittance of such films, which we stop with gold nanoparticles on the top. And you see that we obtain quite interesting situation when we obtain, we have not only pure transmittance of our material, but we have also some impact from interference, because we have thin films, and we obtain just situation when reflection from the different surfaces, interfaces of these films resulted in some interference fringes here. And we thought how to separate influence from interference from the influence of plasmonic. And we propose such solution when we just make normalization. It means when we have pure titanium dioxide film, we take transmission of this film like a reference. And then when we measure transmittance of film with gold particles on the top, we just divide one transmittance with gold on the another reference transmittance, and we obtain such type of dependence. And we think that this dip in transmission corresponds to the plasmonic absorption in gold nanoparticles. And if we model situation, for example, for like an average for spherical particles, we obtain the same shift in light extinction for gold situating inside titanium dioxide, a little bit radius shift with increase of size of particles. And the same in experiment when we increase concentration of gold salt, we obtain bigger particles, and also we have some red shift in the resonance. So we also submitted these results to the thin solid film journal. But let's return to the question how we can use, okay, with absorber we can obtain some influence on absorption, but how it will influence on efficiency of solar cell. Usually when we say about efficiency, we have dependence of current on the voltage. And in this case, in these points we have so-called open circuit voltage, and in this point we have short circuit current. And this is like extreme points, but we will work in between of them. And saying about efficiency, people just multiply this current and voltage and obtain such square, and a ratio of this area inside and this area will give us so-called fill factor. And in case of nice work of solar cell, fill factor will be near like this value. Usually in papers, authors say about increase in photocurrent. It means when they add nanoparticles, they obtain increase in photocurrent. For example, in this paper. But more correctly, if guys see not only on the photocurrent but also on the voltage, because we have fill factor and we must monitor not only current but the voltage. And you see, for example, in this case of addition of silver, these authors say that if we fix the voltage at the same voltages with silver particles, we can obtain a little higher current. So it's nice effect. It means that we don't have losses in the voltage. And in this paper also you see it's a very famous group of Edgewater. They use such type of structure when they use some multi-layered cell, and it was influenced from argentum, which plays here, and they obtain fill factor these values, and efficiency you see difference in efficiency may be 2% maximum. And in conclusion, it's very useful to have like general overview when we will use plasmonics, where we can be in efficiency. So how maximal efficiency can be if you will use plasmons. And here I found a nice diagram in the this reviewing paper. Here you see that increase in efficiency of solar cell is struggle against the losses. It means we cannot have ideal material, or we cannot have ideal structure which will allow us to use all of incident light. But it is possible to struggle against it, to improve the structures, and you see that the most efficient way to improve is this multi-junction solar cell. It means that when you have several layers specially adjusted to absorb some spectral range of light, and these layers just deposit one after another, we can just step by step absorb one region, then in second, then in third, and then more completely absorb it. And you see these multi-junction solar cells can increase efficiency like several tens of %. Then these light directors can also like near 10% can give us. And plasmonics situating somewhere here, it means up to, I think, 5% we can obtain using plasmonics. And the perspectives, I think that if we will combine plasmonics with light directors or with multi-junction solar cells, we can obtain more. So this plasmonic technique can help us in combination with other techniques. And in the end, I just mentioned useful references which give you some details about these topics. And thank you for attention.
Thanks a lot for this overview of solar cell. So we have time for questions now, and especially for questions from students.
Yeah.
So we start with the non-students, then maybe. Okay.
So obviously I understand that when you incorporate nanoparticles in solar cell, you increase absorption because nanoparticles absorb, yes. But if I understand, what you need is not only that, is to be able, with the light that you have absorbed, to create charges.
Yes.
And why is it efficient when you add nanoparticles? It's demonstrated that due to the high local electric field around nanoparticles, charges are created?
Yes, exactly. It means that local field allow locally enhanced absorption, and since you have more effective absorption, you can create more effectively this electron and hole pairs.
But it is due to the electric field. It's not the direct influence is the electric field close to the nanoparticles.
Yes, yes.
The dipole of it. Okay.
Yes.
Yeah, I may add something to that because just that the concentration of light that will just enhance the efficiency. And there were just, when you were talking about the third generation solar cell, there were just a record this summer of the highest efficiency of this kind of multiple solar cell, which is 43%. That's enormous. So with using stack solar cell, stack different semiconductor plus light concentrator. So it's different thing, but 43% is not bad.
Of course, but it's much more expensive, I think.
Yeah, it's much more expensive. See, that's another way. So maybe we have question, yeah, from the back.
At first, thank you very much for your lecture. And it's not a question; it's like a proposition. I know that some physicists has prepared these nanoparticles with these films in another way. For example, they have this core of rare earth metal or something like that, and then cover it for linkers, for organic linkers, and these linkers put here and some another nanoparticles or some another organic compounds. And in case of fluorescence, it should be really helpful. It's that this quantum yield is really big, and by analogy, I think if you use another type of particles when you have these linkers of organic nanoparticles, what do you think? What do you think? It would be helpful to find these really unusual properties which you show now today?
I think yes, it will be very nice, and we need to collaborate more with chemists to do these surface modifications of particles.
Because the problem, because we do really unusual we make really unusual structures, and physicists do really unusual experiments, and I think it's a problem of collaboration.
Okay, thank you very much. We can discuss it after session. So.
Thank you.
Okay, another question.
My question, maybe.
Yeah. Okay.
About aluminium, Leonia, please, why it is not possible to get enhancement with aluminium?
Because aluminium works in more in bluish region. Therefore, it can be plasmonic, but it works more in bluish region. But we're saying about the reddish, about near reddish, near infrared.
Okay, thanks.
Okay, questions? Okay, yeah.
Could you please show one of the last slides when you showed the shift of the plasmonic band with the increase of the diameter?
Right here.
Yes, this one, the right one. Actually, as you show it, the shift seems to be relatively too big. The shift of about 50 nanometers in wavelengths. For gold, it is known that this increase in the diameter from 30 to 50 doesn't give that kind of large shift. This resembles for me, this resembles more the kind of agglomeration of particles, because in the shifted wave you can see a shoulder at about 550 nanometers, and then the second band of shifted band about 650.
But
so
it's
my question is,
okay.
First of all, did you notice any agglomeration of your nanoparticles on the surface of your photovoltaic devices? And the second, what about hotspots? Maybe the coupling of small nanoparticles would give you just the enhancement of local field, which is known in surface enhanced spectroscopy.
Of course, agglomeration can cause such shift also. I think we cannot say exactly how strongly they agglomerate, but according to SEM images, we did not prepare such very concentrated samples where we have strong agglomeration. Concerning the shift, I try to model it using the Mi calculations, and it will be interesting that the higher refractive index of environment you have, the higher red shift you will obtain with the size, with increased size. It means that since here we have high refractive index medium, like for titanium dioxide near 2.1, then I think it can be reasonable, such kind of shift.
I thought it about the water, of course.
No, it's in high refractive index medium.
Okay. Are there other questions? Yeah.
What about full spherical particles, like triangle particles?
It could be nice to simulate them. We just come to this task.
Okay, so I think, yeah, we can close the lecture, and so thanks.